Alright, hello, everyone. I guess we'll give it a couple more minutes. So, today we will be going over the basics of Boolean. So this includes the Boolean values, Boolean algebra, every representation of Boolean you can possibly make, and how to use Boolean to calculate binary. So we're actually going to start off with where we left off last time, so the chapter summary. So a quick summary is that the main components of the CPU instructions includes the opcode and operands. So this includes the instructions, which is the opcode, and the operands, which is the data. And instructions and data are going to be the basics of every single program that you write, and it's also the basics of how a CPU can run everything that you tell it to do. The second point is that data is processed by the CPU. Data processed by the CPU, it can be in nearly any type. It can be a number, it can be a Boolean value, it could be a string. It can so essentially the CPU will eventually everything will just be turned into binary, and so the CPU will just be calculating all these binary numbers and coming up with the final result, which it will then return, and that is what you see in your GUI. And the third point is that everything processed by the CPU is in binary form. So I touched on this in the last point. So binary form is machine code, and so the only thing that the CPU can do is process binary. So this is through the it manipulates through opcode and data. So we didn't get too much into opcode last time, so a quick kind of learning point on it. So opcode, also known as operation code. Um, so operation code, the word operation, it's kind of like instructions. So what you should do. So that's literally what opcode is. It's instructions for the computer. So essentially, opcode is the machine language, which is the binary, that can specify what the CPU is supposed to do. And so here's a quick example of it. You can read over here. So essentially, there's the standard by 86 instruction set, which is the original CPU, and so the opcode is written as 0x10, and so this means add with carry. So essentially, what's happening is the computer or the CPU now knows that it's supposed to this is essentially like what is sent into the processor, so it can be turned into opcode. And so this is the breakdown of it. So you see 0x10 is the assembly code, 0x it's the following hexadecimal. So that means that since this is 16 in decimal, then you just represent it as 16 in binary, and so the it will be sent in as opcode, and so the CPU will recognize that it is supposed to be adding with a carry. Now, now that we know kind of how opcode works, we'll see more examples later on probably. And so this is the basics of how a computer or CPU will run and process everything that you send to it. Okay, so binary addition, we touched on this last time, but I would like to touch on it again because it is a very important topic, and it is very important that we understand this as thoroughly as possible. So as we can see here, here's the example. So essentially, we saw how we could do binary addition. So it's essentially just regular addition, except the only digits are 0 and 1. Now, the way this computer can do binary addition is essentially the binary, the only thing that the CPU can do is actually do binary calculations. So essentially, the computer is just running a lot of binary calculations at one time. And so we in the next couple of slides, we're going to figure out how the computer actually does this. So in order for the computer to actually perform these binary operations, and we need to introduce a topic known as Boolean algebra. Now, Boolean algebra plays a major role in how the computer can perform binary addition. So many of you guys are probably not very familiar with Boolean algebra, so that's kind of what this lesson is going to get into. So Boolean algebra. So I'm sure you guys know what and, or, and not mean in English, right? So we're going to be kind of translating these English definitions into programming. So as we can see over here, we have and, or not over here, and we have these kind of symbols over here, and then we have this table of values over here, and then we have these rules over here that these symbols and values follow, and then here are the actual symbols, and here's a combination of them. So we're going to get into this into more detail. So essentially, these three are the kind of basics of Boolean algebra. You can make every single possible calculation that this computer will ever need to make using these three basics: and, or, and not. And what a truth table is over here is this is what a truth table will look like, and it's essentially a table of inputs and outputs. So you put two inputs in, it will give you the output. And so a truth table is essential in debugging and figuring out what the possibilities are because of how it can cover every single possibility, because you use every single input possible and you give its output. Now, as we get into Boolean algebra, these three symbols, you should know them. It's not entirely too important to know them by heart, but you should definitely get familiar with them, as although you won't actually need Boolean algebra in your real life, you or programming, as a matter of fact, you will need to kind of know this in order to understand how the computer works and how the computer performs these binary calculations. So just take a look at these for 1 second, and I will start talking about these truth tables. Okay, so now that we've looked at these, so this is going to be the inverter, or the not. This is going to be and this is going to be or. So the first thing that we're going to look at is and. So and has 4 different possible inputs: 0, 0, 0, or a false, false; 0, 1, false, true; 1, 0, true, false; and 1, 1, which is true and true. Now, the basics of and is essentially both of these values have to be true in order for the output to be true. So if any one of these is a 0, then it's automatically false. So we look at 0, 0, we look at 0, 0, and we get a 0 because both of them are false. We have a 0, 1, and since A is false, then we get the output as false as well. We get 1, 0, and since B is false, the output is false as well. But since A and B over here are both true, then that means our output is also true. The next thing that we're going to look at is or. So or essentially means if at least one of these is true, then the output is true, no matter what the other value is. So we have 0, 0 over here. Since both of these are false, the output is false. We have 0, 1, and since B is true, that means the output is true. We have 1 and 0, and since A is true, then that means the output is true. And since A and B are true in the last case, then C is true as well. And finally is going to be the inverter, or the not. So essentially what this not function does is it reverses the value. So if it's false over here, like a 0, it turns it into 1, or true. And if it's true, then it turns it to false. So this is kind of a English representation of what's kind of happening in each one of these functions. So you can take a quick look at that. So now that we've had a good look at that, so moving from this function to this function over here, so we have or, and, not, and so or, and, not, they can make all 3 of these. So XOR, which stands for exclusive OR, essentially means that one of the values has to be true, but both values cannot be true. So essentially, the only true cases are going to be true, false, and false, true. But if you have either true, true, or false, false, then it will return false. Then we have NOR. So NOR is essentially a combination of not and or. And so finally, we have NAND, which is a combination of not and and. And we're going to get into more detail in this a little bit later, but this is kind of a simple representation of what these functions can kind of do. So Boolean logic, in real life terms, it's always easier to see it if we can have something that we can kind of compare it against. So for the AND gate, it's kind of like a safe deposit box in which you're going to need 2 keys, or both of the keys, in order to unlock each box. Now your home entrance is going to be an OR gate because you only need 1 out of the many keys to your house in order to open up the house. or the door, sorry. And finally, there is the whining kid or the not gate. And so this means um, you can't talk to a whining kid because they're always going to say no to you. So Boolean logic is it's often compared to with the Venn diagram. And the reason for this is because the Venn diagram is a very visual representation of Boolean logic. So here we are, we're going to take a quick look at it. So we have the AND function over here. So the AND function is going to cover the overlap of the two circles, and so only the overlap is going to return true. Now we have the OR function, and so anything within those two circles will return true. The NOR function is essentially the exact opposite of OR, and so everything outside of the two circles will return true as well. And finally we have XOR, or exclusive OR, and so this will return everything except for that overlap in outside the two circles. Okay, so the NAND logic gate. So the NAND logic gate is built by NOT and AND, as you can see right here. And so if we see over here, we have A, B, and then it goes through these logic gates, and so this is what the output would look like. You don't actually need to know how these characters get transformed into everything, but this is what the NAND logic gate would look like if you're using AND and NOT. So if you were to use try and build the XOR from NAND, so the reason why NAND is actually so special is because of the fact that NAND is actually kind of like the basic function. So after you have AND, OR, and NOT, NAND is the next most important logic gate, as it is used to build other logic gates like XOR. And so this is what the XOR logic gate would be built like. And so essentially what the XOR logic gate needs to make sure that it covers is that it needs to make sure that it will always return false if both of the values return true, and it also needs to remember to return false when none of the values return true. So you can try and follow this logic gate over here. I'm not going to go ahead and explain it. It requires a little bit of thinking, so I'll leave you guys to look at that for a second. Okay, so now that you guys have had a good look at it, we'll go on to the next slide. So we have Boolean logic and binary addition. So this is kind of a summary of what we've learned so far. So if we look at this carefully over here, so we have 1 and 1. And so essentially, in order to add these two binary digits together, if we were to just look at this column, then we would see that this is actually I'll let you guys think about it for a little bit. So as you can see, if you were to have 1 and 1, then you would have 0. So we're going to ignore the carry here for a second. So we just have a 1 and 1, and it returns a 0 right here. So if we look at the other cases, if we have 1 and 0, or 0 and 1, then they would both return 1. However, if we have a 0, 0, then this would also return 0. So essentially, this is the XOR logic gate, or the exclusive OR. So the only cases in which the output will be 1 is when either one of the values is true, or 1. But if both of them are the same value, then it will return a 0. So here we can see this logic gate of the XOR over here. And so as for this carry over here, so essentially the only case in which there will be a carry if there is an AND. And so this will bring us into the ideas of a half adder and a full adder, which we will cover later on. But essentially, this is your first kind of application of these new logic gates that we've learned. So you guys can look at this for a second. So there are many other cases that can exist. So for example, when there's a carry, then that means that instead of just 2 digits that we have to look at, there are now 3 digits that we have to look at, because we have to think about what the carry would bring. Alright, let's go into the next slide. So, as I said before, the half adder and full adder. So we're going to look into the half adder over here. So the half adder over here is essentially, we have 2 inputs, A and B, and it will essentially put out the output, and it will also have the AND gate for the carryover to the next digit. So this is useful when you're trying to add 2 binary digits and you do not take into account of the carry from the previous addition. So essentially, in this example back here, if you were to add these 2 together, then you would not, you completely ignore this carry over here. So that is why it's called a half adder rather than a full adder, because, well, it only accounts for kind of half of the information that is needed. So, as we said before, there's the XOR gate for the outputs, and there's the AND gate for the carry. So this is a fairly basic idea. So we're going to move on into the full adder. And so the full adder kind of looks a little complicated, so we'll kind of do a little run through over it. Or actually, the half adder truth table, this is probably a good thing to go over. So essentially, instead of just having to worry about the sum, we also have to worry about the carry. So this is what the half adder looks like, and so you can just kind of look at this input-output table. Alright, so now that you guys have had a good look at this truth table, I'm sure you guys see this diagram over here, which is the full adder. So let's move on to that. So the full adder. So we're going to spend a little time here because the full adder is, it's kind of complicated. So essentially, not only do we have to consider the 2 digits that we have, but we also have to consider the C in, or carry in. So the carry in, so if we look at it over here, we're going to have the XOR, and we're going to have a second XOR in order for us to see the sum. And so this would make sense because it kind of shows us that if there are ever any cases with 2 1s, then this means that we're going to have to kind of if there's ever 2 1s, then there is always going to be a 0. So we can kind of pause here and take a look at the sums over here. Now that we've looked at the sum, now we're going to go look at the carry out. So the carry out is going to be slightly more complicated. So as we've seen over here, we can see the AND function over here. So we go from here and we grab A, and we grab B, and it comes over here, and we have an AND. So after this AND, so if both of them results have 1, then this will be a 1. And so we come over here, and so we look at this, and we take carry in, and at the carry in, it will kind of go over here to this part of the and over here where we have this XOR function, it will also push a value into this AND function. And so essentially what this means is that if this is 1 and 1, or so if this is 1 and 1, then that means that it will return a 0, and so it just kind of completes the XOR function. And so after it brings its two values, then it can show either a 1 or a 0 at the end. And so at this point, it will always carry out as long as one of these will return as a 1, because they both will not fit inside the regular sum digit. So this is kind of the full truth table, and it will show all your inputs and outputs. And so as we can see, there's a lot more combinations that we can come up with. Alright, so now that we've kind of seen this truth table over here, and we can see all these inputs and outputs, now we have a much better understanding of how the computer can do all these binary calculations. So kind of like a chapter summary of this. So we talked over a couple of the logic gates. So this includes the 3 basic, as well as the other logic operations that we can form from this. And so first we have the OR, AND, and NOT. So these are kind of ones that we can use in everyday life, and we kind of encounter these all the time. And then we can build these into slightly more complicated logic operations. So this includes exclusive OR, NOR, and NAND. And so we've also seen how these kind of work in our half adder and full adder. We've also seen that NAND is the most important one, because almost any logic operation can be built with a NAND gate. And so we saw how it could build the XOR gates in that slide. And finally, we can kind of see how binary addition can be done with the AND and XOR gates. And so this includes both the half adder and the full adder. So now that we've kind of had a basic look at this, we can kind of look into more detail of the more complicated ones, I guess. So we can come over here. So there is a site. Tutorial point. Okay, so this is kind of a great summary of all of the logic gates that we've kind of gone over today, and it also includes the exclusive NOR gates. So we're going to go into that in more detail. So I'll put the link into here, so you guys can open it as well if you want to. And follow along. So we're just gonna kind of quickly go over these. So we have the AND gate. We've already seen the truth table, the logic diagram, and the circuit, and the AND operation. We've seen the same thing with the OR and the same thing with a NOT. So we saw this with the NAND gate. Now finally, we haven't kind of taken a closer look at these. So the NOR gate. So this is kind of what the NOR gate is built out of. So we have the OR and the NOT, and so essentially it takes the OR and it flips the value. So for OR, the output would be 0, 1, 1, 1. However, since this is actually a since this is uses a NOT gate, then it just flips every single value. So it returns it as a 1, 0, 0, 0. So we can look at this for a second. . Alright, so next is the XOR gate. So the XOR gate, exclusive OR gate. So we kind of looked at how it was built, and so this is what it will look like. And essentially what's happening in this one is we saw it in action in the half adder and full adder. And so if either one of these is 1, then we can return 1. However, if both of them are 1, then it will return 0. And finally is the XNOR gate, or the XNOR gate. And so essentially, so this is what it will look like as a logic gate. And so what it does is it takes the XOR gate and it flips the value. So kind of what the NOR gate did over here. So we can see both these truth tables. So normally it would return 0, 1, 1, 0. But the XNOR gate essentially just flips it entirely. So instead of returning 0, 1, 1, 0, when both of these are 0, then it will return a 1. But if either one of these is a 1, then it will return a 0. However, if both of them are 1, then it will also return a 1. So that kind of wraps up the lesson for today. If you have any questions, feel free to ask them right now. If you don't have any right now, and you kind of think of some other questions later, then you can always come to the office hour, which will be next Thursday, I believe, at 4 p.m. Thank you for listening. So it doesn't. Oh, does anyone have a question?
No. Thanks for clearing it out, Ken.
Isn't it on Wednesday?
Alright,
The
thank
office
you.
hours? Okay, I guess not.